Hello, and thank you for joining me today for this webinar, which is all about 4 real ways AI is going to transform testing over the next 2 years, and why actually all these are good reasons for testers. My name is Anthony, and I'm the CTO of Eggplant. So AI is clearly the big topic in testing this year, with every other sort of webinar, blog, or conference talk talking about it, and obviously I'm no exception. But I find that whenever I go to a talk or a webinar on AI and testing, I tend to see a lot of pictures of cyborgs and stylized brains, maybe a video of an Alexa or a self-driving car, but I don't really hear that much about what AI actually is and how it's going to impact my testing over the next 2 years. So I'm a tester. I'm sitting here, I'm writing scripts, I'm running tests, I'm setting up environments, I'm reviewing results. And I can see that in the future, apparently all this is going to be done by the Terminator. But between now and then, what's going to happen? What are the steps that are going to get us there? Sure, we can use TensorFlow and the like to work out that a picture of a dog is a dog, and I can use a simple neural network as a good way of repairing broken XPaths. But is that it? I don't have that many use cases that require telling me that a picture of a dog is a dog. And fixing up broken XPaths seems a long way from fully automated, realistic testing. So today I wanted to talk about 4 concrete ways AI is really going to transform testing over the next 2 years and go into a bit of detail. And my purpose here is really to help you get through the noise and get started with AI in testing, making use of the cool real stuff that is available now. And I'll be talking about some of the things you can start doing tomorrow without buying any new products. Help you start formulating a plan for how you're going to use these new technologies to transform testing in your organization, and also convince you that these transformations are good for testers and people who enjoy spending their time creating great software that delights users and drives business outcomes. So let's go. And here is the first cyborg. Now, before I get into the ways AI and analytics are going to transform testing, I do want to spend a bit of time defining what I mean by AI, because it's clearly a really broad area and it's got a lot of noise, and people use the AI label to mean everything from, what is effectively an if statement, all the way to sort of self-aware cyborgs. And I think that's part of why people find it so hard to understand AI, because they hear people talking about outcomes and results that sound like it's the cyborg end of the spectrum going on, but then they look at the technology, and the technologies look more like the if side of things, and there's a real disconnect there. And I think a lot of AI presentations kind of follow that format. So let's define what we really mean here and be consistent. So this talk is all about how AI is really transforming testing now and over the next 2 years. And so my definition of AI is really practical. And today, I think at a practical level, AI really means learning algorithms, neural networks, and deep networks. Now, what are they? Learning algorithms are really simply algorithms that take history into account. So for example, in this case, I have an algorithm that categorizes a change as risky or not based on which developer made the change. Now, a traditional algorithm would simply have some sort of static rating of developers, whereas a learning algorithm is going to look at the submission history, which is constantly updating and changing, to determine whether a code change is risky. So whereas a normal sort of traditional static algorithm just uses sort of one-off definitions that are hard-coded, a learning algorithm uses the data available and the constantly changing data available to make a more dynamic, more up-to-date, and usually more accurate decision. Neural networks are obviously a more advanced form of AI, and it's hard to explain them really quickly. So I'm just going to give a very high-level explanation, and hopefully that'll be enough to sort of have the rest of this presentation make sense. But basically, neural networks are a way of identifying patterns between inputs and outputs. So you give the neural network a set of input variables, in this case, the performance of individual pages of a website. You give it an output variable that you care about. So in this case, whether the user bought something from the website. And the point of a neural network is to reverse engineer what the relationship is between those inputs and those outputs. So in our case, understand the relationship between the performance of these different web pages and whether someone buys something for your site. And the benefit, of course, is then you can use this to predict the output for the future, depending on how those inputs may change. So you could then predict what would happen if the performance of the homepage went from 2.1 seconds down to 1.4 seconds. Deep neural networks are a more complex form of neural networks. Basically, they have multiple layers, and that just really increases the complexity of the input variables and the relationships you can have between those and the output variables. So if you just think about it as a more complex form of neural networks, I think that's good enough. Okay, so these are really the technologies that I'm talking about when I say AI. Everyone always loves to have the is it real AI or not conversation, and it's not really intelligence. All those are valid, but here, when I say AI, please just bear with me that this is what I mean, this is what we're talking about, and we're looking at how these technologies are going to transform testing. Right, so the first way AI is going to transform testing, and the one people talk about the most, is the auto-generation of test scripts. Now, I hear a lot of cynicism about this, which I guess is fair because it sounds pretty magical. And I think the key here is simply to acknowledge that in the next 2 years, we are not going to be at a point where we completely auto-generate every test for any system without any human intervention whatsoever. Clearly, that's just not going to happen. But it's not all or nothing. I think in the testing world, we have a tendency to polarize these discussions. I mean, I think the manual testing versus automated testing debate really kind of held us back for about 10 years while we argued about which one was better, where clearly the reality was a mix of both is the optimal. And it's the same here for the moment. Over the next 2 years, I think the optimal scenario is going to be using a combination of these great new technologies that can auto-generate a large part or a significant part of your scripts, but that's still going to be mixed in with some human effort. So yes, human effort's still going to be needed to write the scripts, but doesn't mean that AI can't massively reduce the amount of time and effort you spend doing that. So here's an example on your screen. This is actually our product, Eggplant AI. Some of you may be familiar with it. And what you see here is a model of the Citibank mobile banking app, and we're dynamically generating user journeys and validations through that app, as you can see on the right. So it's a real device over on the right executing those test cases. So just to explain it a little more, if you look at that model, those large sort of purple blue boxes, they correspond to the different screens on the application. Within those screens, you have the little gray boxes. They are the actions that a user can perform on those screens. Now, it's important to note that these are not what I would call micro actions, sort of, click, type, tab, move mouse. These are really what I call user level actions. So they're the sorts of things a user would talk about when describing how they use an application, entering their username, entering their password, signing on, going to their profile, changing their account number, sending a text message, rotating the screen. These are the kind of actions we're talking about here. Okay, so we have some model-based testing, but where's the AI and all that? Well, really they're in 3 places. The first is in the ability to auto-generate the model itself. The second is the auto-generation of snippets, which I'll come back to. And the third is the generation of the validation points. Now, I should have said before when I was describing the model, we have these user level actions. At some point, of course, that does have to be translated into micro actions. The click here, look for label, move to the right, press tab, press button, press enter. Those are what we call snippets. So under each of these user level actions, which are the gray boxes in the model, you have attached snippet, which is the thing that actually knows how to go and execute that on a real device. And so part of the AI is to auto-generate them. Okay, so how does all that auto-generation work? Well, there are a few different approaches, but I think the core principles are the same, and the clearest to explain it in is actually these snippets for UI tests. Now, I should say that the principles I'm going to talk about here also hold for unit testing or API testing. In fact, in a lot of ways, those are much simpler because they're much more formalized, constrained environments. But the presentation is just much more interesting if I show it with a UI. So the way the auto generation of snippets works is we use the model to navigate around the application, and we get to a screen. And then we use various techniques to understand the UI at the control level. So on the screen there, you could see we were using OCR and intelligent image recognition to understand the different controls on the screen. We can also go to the DOM, and we do already use a neural network to understand the type of the control. For example, whether, not just whether it's a button, but is this a submit button, or is this a help button, or is this a cancel button that moves backwards? Is this a navigational button? Is this a data button? Understand things like flat images versus interactive images, and so on. Now, once we understand the controls and the type of those controls, we can start auto-generating the basic handlers, and that's something you would have seen on your screen as that video played. So if it's a button, we can generate the handler to click on the button. If it's a field, we can fill out the field, we can put text in, we can read the current text in there, and so on. And I would say that that ability to just auto-generate those basic handler functions is already pretty useful and already a good start in terms of auto-generating scripts. But once we've got that, we go to the next level. So we take our neural network, we let it know what are the controls on the screen, how are they arranged, and so on. And you can start to understand different types of screens. There's things like there's the form, there's the information screen, which is really just a whole lot of text followed by a sort of yes, I understand or a next button. You get the menu screen where you've just got a bunch of options that you're selecting from. You get, a palette, which maybe you can draw on, such as the Eggplant AI screen here. So we can start to understand the different types of screen. Again, we're taking advantage of the fact that, UI design, although obviously there's uniqueness about it all, there's also a lot of standardization. We're all used to conventions. We all would expect sort of the properties panel to be on the right of the screen and the navigation panels to be on the left of the screen, exactly as we have here. And so we can use that to then start generating higher level functions such as, fill out the form, verify the screen, select items from the menu, draw something on the palette. Okay, and then we can start combining these handlers at the screen level into flows through the application. So you can go into things like login, fill out patient details, send email, play the level of a game, whatever. And that's basically the fundamental process. It's a very layered approach. I think that's a key concept I'm trying to get across. People often think, well, how would I go from, knowing that there's a button here to suddenly, going into Amazon and searching for a product and buying it, or finding an aeroplane course through a GIS system. But that's not what we're doing. We're really building it up layer at a time. We first understand what are the controls, what are the elements of the screen. Then we try and identify what's the nature of this screen. And then we try and understand what's the flow through the entire application. And we build those up step by step. We do that using neural networks where you have lots of different inputs. So the UI itself, you have the code, you have natural language parsing of code. It's a really interesting area that I'd sort of encourage people to look at. It's amazing what you can glean from code, not from the syntax of it, but just the comments and the names that the developer has given to the variables and the function names. User stories are obviously a great source of flows. Test cases are a great source of flows. App logs, all sorts of things. And of course, at every stage of that, as we're building up these test cases, we could get it wrong. The moment the screen or the flows start deviating significantly from standards or from what it's seen before, we may not be able to correctly auto-generate the script. And that's again where you're going to need the intelligent tester to either train the AI better or just correct it. Now, the process for generating the model and the validations are a little bit different. They've got some interesting nuances, but most of the principles are the same. And so in the interest of time, I'm not going to go through those right now, but obviously be happy to talk to anyone about those if you're interested. Now, the last thing before I leave this topic, what I've described here so far is representative of, I think, the main approaches I've seen to the auto generation of test scripts. But there are some other interesting approaches. And just as an example, I wanted to show this example from MoQuality. So they have a really interesting approach to actually helping people do game testing using AI. It's a really simple approach. So if you think about the neural network, they keep it really simple. The inputs are simply the controls that a player can have: up, down, left, right, B, A, jump, shoot. And the output variable is simply the score. So what we're trying to optimize here for is the score. And it watches people play and it learns what are the combinations of keys that tend to make the score go up. So let's do that. And I think it's a really cool idea. I'll be honest, it doesn't really work. The problem is the sequences of buttons are too long. They're not repetitive. The same sequence in this place is not going to work in the other place. In a game like Mario, you can get somewhere because in general moving right is a good thing to do. And when you're pressing the right button and not going any further right, it's probably a good idea to jump. But if you think about it, and if you've played Mario, know that that'll get you some way, but it's not going to get you all the way. So it's not it's not the answer. But I'm putting it up here to say, firstly, that there are other approaches. There's still a very active research area, and there's lots of interesting ideas coming up all the time. And I also think this is really interesting in how simple they've kept it. I think over the years, testing's gone deeper and deeper and deeper. Sort of, it's almost proxies to proxies to proxies. And I love the fact that these guys have just gone totally back to the raw element. What I care about is making my score go up. My inputs are just, basically the keyboard, and go from there. And I think that's really interesting. And I think that kind of back to basics thinking almost so important when you're dealing with AI, and I think so important to the future of testing. Okay, so we can now auto-generate automated test execution scripts. Isn't that wonderful? And I can actually remember when we first got a prototype of this working about 2 years ago. We were working with a team at Amazon, seeing how this approach would work on the Amazon shopping mobile app. And that's it on the screen here. And it may look quite small, but including data, you can actually generate 9.2 billion different user journeys from this app, which of course we thought was great. With so little effort, we're able to generate 9.2 billion tests. It ended up as something like, sort of 1,000th of a second per test case we were writing. That's great. But then, of course, they asked us, well, hey, even Amazon can't run 9.2 billion tests in an evening. We can probably run a few thousand. So which tests should we run? We've got 9.2 billion tests now. Which 1,000 should we run? And it's a really good question, because the bottleneck for test automation forever has been our ability to create and maintain scripts. The question doesn't really come up, which ones should we run? We'll just run all of them. And of course, we do have smoke tests that we run on check-in or something like that, but that's okay because we've only got a few hundred tests, so handpicking sort of the 20 or 30 that matter is easy enough. But when you can auto-generate 9.2 billion tests, suddenly this becomes a big challenge. Now, of course, there are existing approaches to test optimization. I mean, risk-based testing is widely talked about, especially for optimizing manual test execution. But the whole risk-based testing approach is a bit manual. I think some of the data's not quite rigorous enough to scale to this level, and the whole approach at the moment, whilst in theory great, I don't think really scales up to be usable for 9.2 billion test cases. The other common approach to test optimization is equivalence classes, or what some people sometimes call coverage, such as pairwise coverage. So in these approaches, you basically decide that a set of user journeys are equivalent, and therefore you only need to test one of them, and you've effectively tested all of them. So for example, you may decide that all the test cases that do a login and make a purchase are equivalent. They're the same. So you only have to do that once, and if you run one of those tests, and let's say there's 1,000 of them, then you've got 100% coverage of those 1,000 tests by executing those one. Now, these approaches can indeed be useful, but they definitely also have some pretty major flaws. And I think the best way to explain this is to think about a game of battleships. So hopefully most of you have heard of the game of battleships and have played it. Unfortunately, if you haven't, this slide's probably not going to make a lot of sense. But unfortunately, I don't really have time to explain all the rules. So hopefully you've played it. Imagine you're playing a game of battleships, but you don't play the normal way. Instead, you choose the exact same squares in the same order every single time you play, and you don't pay any attention if you get a hit. So, if you say D4 and they say hit, you just keep doing the same square you would have anyway, even if they'd said miss. And let's say also you've only got a limited number of pegs because you've decided that's how you're going to play. So you're doing the same squares every time, you're ignoring any feedback, and you've got a limited number of pegs. Now, I think if you played battleships that way, you would lose. You would lose. And it's not that far off in testing with these equivalence class approaches. They're very static coverage approaches, so they definitely hit the exact same test cases every time. If they hit a defect, they don't suddenly decide, oh, actually, I've run one of the test cases in this equivalence class and it's found a defect. Maybe I should run a few others to see if I can isolate the necessary and sufficient conditions. Or maybe I might find other defects in the area, because bugs definitely have spatial locality. They don't do any of that. They just keep executing the same tests every time in the same order, ignoring all feedback. And once they get to the end, even if you've got a couple of hours left where you could do more testing, they just stop because that's what they do. So they're definitely useful, and we use a lot of coverage models in the work we do, especially during the training process. But even when they tell you have 100% coverage, we all know there's still plenty of defects left in the code. So we need a new approach to deciding which tests, which user journeys we're going to run. And again, this is somewhere AI is going to transform testing. And it's actually appropriate that we just spoke about Amazon, because the core concept here is to create a recommendation engine to decide which user journey, which test we're going to run next. So how does a recommendation work, or recommendation engine work, sorry? And specifically here, I'm going to talk about knowledge-based recommendation engines rather than content filtering or collaborative filtering, which are other approaches. It just so happens that knowledge-based filtering and recommendations, I think, work very well in testing, so that's what we're focused on. So how do they work? Well, let's say we've got a stack of books and we want to decide which book to read next. Well, what the recommendation engine does is it gathers a set of data, a set of attributes about each of the books available. So it's things like author, genre, length, year published, etc. It then looks at all the books you've previously bought or shown an interest in. So it gathers all those books. It uses those attributes as the input into the neural network, where the output is, books you cared about, books you had an interest in, and then it uses that to identify the book that is most likely going to match your preference next, right? So the input to the neural network are the attributes of the books, The output is whether you like a book or not, and it uses that to look at all the existing books and predict which one matches your criteria the best, right? So that's how a recommendation engine works. What does that look like in testing? Well, once you're in testing, books basically are the individual test cases. The attributes of those test cases become a whole lot of information about risk variables from the software development process, such as whether this user journey has been impacted by a recent code change, what the underlying technology stack is. C++ code has more defects than Java code. Who made the change? So developers very familiar with an area of code tend to make fewer defects than people who are new to code. Interestingly enough, the people who are worse to be in the code are people who used to edit it but haven't done it for a while. Also looking at things like when in the sprint the change was made. Changes made at the end of sprint cycles tend to be far more buggier. So that sort of stuff. Risk variables from user journey itself, such as whether it went to a very busy screen, whether it made transactions, whether it's going back and forward in a control path, and how much parts of the user journey have already been covered by previous tests, so what kind of coverage we have there. So we gather a huge amount of information about that test, how the code was created, what that user journey looks like from a product user level, how much testing has been done. The recommendation engine then looks at the tests that have already been run, whether they've passed or failed, and it uses a neural network to find the attributes that correlate with a test failure. So the inputs are all those attributes of tests. The output is whether a test passed or failed, like whether a bug was found. It uses that to find out what attributes correlate with failure. It looks at all the remaining tests, and whichever one matches that criteria, most likely to find a defect, we select that one and we run it next. And that will, of course, either find a bug or not. That then feeds into the neural network, and the neural network is learning. So the more testing we're doing, the more accurate our predictions get. And that's how it works. Incidentally, those who are interested in this kind of stuff, I find this sort of thing very interesting. There's a fantastic book called Recommendation Systems in Software Engineering. It's quite an academic book, but if you really want to get into the details of how recommendations engines work, how AI works, and how it can be applied really to software engineering as a whole, I think that's a fantastic read. So that's how it works. Essentially, we're using a neural network to do risk-based testing analysis in a structured way, and then a knowledge-based recommendation engine to select the next test to run. It means that at any point, I'm executing the next most likely test to find a defect. And that's what testing is all about, right? And it's really important to notice, some people look at this and think, oh, that's very thorough. That looks like it's only for big bang testing. But no, even if you've only got time to run one test, this will select the best test to run. If you've got 5 minutes to test before a code submission has to sort of be accepted or rejected, this will select the best 5, 10, 50, whatever you got time for, tests to run. So no matter what your testing window looks like, this is definitely the best approach to be using. Right, the third way I think AI is going to transform testing is release analytics. And I'm going to start here with an example, and you'll be very pleased to hear that it does not involve a neural network. So this graph is from a trial we did with a retail customer of ours in the US, actually. It was Walmart. And they wanted to just improve how they were doing release management. Right, so what we did is we created this tool. And what we did is we took all their releases from the last 2 years. So those dots and triangles are their releases. And we plotted them on this graph where on the x-axis we have the amount of testing done. And actually for the first version of this, all we did was people days of testing, so nothing sophisticated. On the y-axis, we have the amount of change that went into the product, just measured by lines of code. So again, very simple. And then we classified each release as either making customer satisfaction go up or down. So the blue circles mean that customer satisfaction went up in the opinion of the product manager and the support team. And the red triangle means that customer satisfaction went down, right? And so what we did is whenever a new release candidate came up, we plotted on this graph, and we used what's called Bayesian classification algorithms, which fundamentally just look at the other sort of samples in your area and decide that whatever is the most prevalent type, you're going to have that same type. So we look at release candidate 1, we say the 5 nearest samples are all releases that made customer satisfaction go up. So if we release that 1, it'll make customer satisfaction go up almost certainly. So that's great. Looking at release candidate 3, we look at that and we go, well, that actually looks really risky. A lot of the other releases in that area made customer satisfaction go down. So that makes us nervous. So what we should do is we should do some more testing that will move it to the right, that will move it more into a zone with blue balls, i.e. customer satisfaction went up, and that's good. So we did about 4 more days of testing on release candidate 3, and that was good. Release candidate 2 is actually really interesting because what we see there is actually there's almost a fundamental limit of change. And if we do more change than that, actually customer satisfaction will go down no matter how much testing we do. So we look at 2 and we say that even if we did a bunch more testing, we still think customer satisfaction would go down because customers just don't like that much change. So what we did with release candidate 2 is we chopped it in 2. We did like 1 or 2 days more testing, just sort of to test the new sort of cut down version of 2. We released that. That made customer satisfaction go up because we reduced the change. And then we released the second version of it about a week later. And again, that made customer satisfaction go up. So this is an example of using some very, very basic sort of analytics, Bayesian classification algorithms, which are very simple but very effective to massively improve the quality and how quantified our release decisions are. And really the point of this example is just how unsophisticated it is. All the metrics I'm using here, this is all data that you guys probably have today. You know, how many days of testing went into this release? How many lines of code changed? Do we think that release went up or down? It's really simple data. It's really simple algorithms. You could do it in a spreadsheet. There's no neural networks here. This is very basic learning algorithms. And yet, the results have been really impressive. It's been an amazingly accurate tool for predicting whether a release is going to make customer satisfaction go up or down. So imagine what we could do if we gathered all the information we have today, not just these 3 bits of information, but all the information we have today from the software development process, from our testing, from previous releases, and we input that into some really sophisticated AI technology. You know, we could start making accurate predictions on the number of defects that will be found by customers post-release, how this is going to perform, what the usability is going to be, and ultimately the customer satisfaction. I mean, imagine how that would transform your average release meeting and the role of test in that meeting. So today in most release meetings, you know, the test team often provide data around things like what's our coverage, what's our pass rate. But often people have, including us as testers, have a lot of trouble translating those data points into, you know, how's this really going to impact the user? How's this going to impact the business outcomes, you know, our business KPIs, our revenue? You know, we have a lot of trouble translating those sort of very test metrics to answer the question of, look, should we release now? Yes or no? Should we release? You know, I don't think test is necessarily, you know, answering that question in meetings today, but I think we have the data, and I think we have the analytical tools these days to answer that question. And I think it's a huge opportunity for test teams. We could also use this to identify the underlying risk factors for releases. So in determining you know, how this is going to impact users in production, where we're sort of by definition identifying what are the risk factors that are really impacting users, via our recommendation engine. And we could take that and we could feed that back into development. So for example, we've determined that with several customers that if you have more than 2 developers in the same code, your defect rates go way up. We found, I think I mentioned earlier, any code submitted in the last 12 hours before the end of a sprint is almost certain to have defects, especially if there's a commercial milestone related to that sprint milestone. So we're reverse engineering these risk factors, and we can take these insights, again, not only to find defects, which is what I've been talking about so far, but helping ensure that defects don't get injected in the first place. And then you start getting into that distinction between testing and quality, which I think is often a bit nebulous, but we're really starting to quantify it here, and we're starting to show how using some of these analytical techniques, testers can not only be answering the business question, but we can also be going on to the full quality question and not just finding issues, but helping people work out how to solve them and how to prevent them happening in the first place, which is pretty exciting. The fourth way AI is going to transform testing, and really the most exciting one for me, is a new area we call customer experience insights. So what is customer experience insights, or CXI? So CXI is all about quantifying how the technical behaviors and attributes of an app or a website impact users and business outcomes. So the example I used earlier when I was explaining neural networks is a great example of CXI. We're quantifying how the page load speed of different parts of your website impact conversions. So how does it work? Well, at a high level, we start by gathering as much information as we can about users, user journeys, business outcomes, or conversions. So, whether someone buys something from the website, whether a doctor fills out patient records within 10 minutes of a consultation, whether 60 planes land within a certain time period in an airport, the predictability of that air traffic control system, the accuracy of mapping applications, did I reach the destination in time? Whatever that conversion is, I think people naturally go to sort of retail dollar type of conversion, but a conversion is whatever you're trying to help people achieve with your software. So we gather all that information and we know a lot of stuff about what users are doing and when they're converting. At the same time, we gather as much information as we can about the technical behavior of the system or the application. So response times, exceptions, usability heuristics, CPU usage, etc. And then we use quite a few different techniques to quantify the relationship between these two, i.e., how are those technical behaviors of the product driving and influencing the business outcome? So in particular, how do the things that we can actually do something about, i.e. the technical attributes, impact the thing we really care about, which is the user behavior and the outcome? And as I say, I think this is really exciting and has the ability to fundamentally transform, well, not only testing, but all of software development. I mean, a long time ago, we used to talk about verification and validation, right, in testing. Verification was whether the product complied with its specification. Validation was whether it was fulfilling its purpose. Basically, did anyone care? But somewhere along the way, we sort of forgot about validation, and we've just become obsessed with verification and actually ever more sort of verification for verification's sake. We'd rather sort of test something that we're sure we can verify than test something that that people really care about but is a bit more difficult. And especially in a world where none of us have specs anymore anyway, it's quite curious. And actually, I think this is the core of that gap between testing and the business that we always talk about. Because what the business cares about are the outcomes, customer satisfaction, conversions, revenue. In our terms, they care about validation. But testing and monitoring these days, more and more, in fact, are all about verification. And I think that's what we need to change. A great concrete example of the gap between verification and validation is defect triage. So we recently ran a trial with a friendly customer of ours, and we applied our CXI engine to defect triage. It was super interesting, and I'll really summarize it in 2 defects. So first, we had a defect which was an exception on their website. And of course, it had been classified as a critical defect. And I'm sure all of you would expect it to be classified as critical, and I'm sure there's sort of a lot of people nodding right now. Makes sense. The second bug was a UI issue where 2 buttons were in the wrong order. And that had, of course, been classified as a low defect. We all classify UI defects as low. I'm sure everyone's sort of still nodding. But, although that made perfect sense to everyone, when we applied CXI to these defects, we found that the exception was impacting 1 in 2,000 user journeys. And whenever a user encountered this issue, all they did was hit the refresh button and continued on their way. And when we spoke to those users, most of them assumed there had been some sort of intermittent network issue or something had happened. No big deal. This defect was having no impact on their business results because 1 in 2,000 people impacted and they just hit the refresh button anyway. But we all just classified that as a critical defect. At the same time, those 2 buttons that were inverted, they were the submit and cancel buttons on a particular screen. And 15% of their users were getting to that screen and pressing the wrong button and going back to the home screen, wondering what had happened, and either just giving up or going through the process again. But if they went through the process again, I'm sure they were pretty upset about it, not very happy. This was having a huge impact on their conversions and their customer satisfaction. But we all just, again, classified it as a low defect. So here we have a great example of where our very technical approach to classifying defects is entirely at odds with the business impact of those defects. And by applying this sort of CXI concept, we can start focusing our defect triage, focus our testing on the business impact, and reduce that gap between testing and the business. And I think this kind of thing, this concept of bringing users and bringing business outcomes in a structured, quantified way back into the development process and all parts of the development process is really going to be the next stage of the whole agile DevOps continuous delivery evolution. It's just natural that the next step is to bring in those guys into the process. Now, all this is probably starting to sound a bit fanciful to you and not like something that's going to impact testing in the next 2 years. So let me show you a real example. So here on the screen, we are looking at some data about the Cook website. And for those of you who don't know, Cook is a food retailer with around 450 stores. And here you can see that we've been monitoring a mix of metrics such as conversions and revenue, and also technical metrics such as page load time, page impressions, bounces, and so on. And obviously this is quite a simple view so that you can understand it, but you can imagine that we're actually gathering hundreds and hundreds of different variables. And so we take that data and we use it to create a model of how performance, mainly load time, impacts revenue. So we can now predict the impact on revenue of improving or worsening the page load time of all the different pages on their website. And that's what we're doing here. So you'll see we're going to say what would happen if we reduced the page load time for a particular page from 2.78 seconds to 1.5 seconds. So we reduced it by 1.28 seconds. And it tells us that we would increase revenue from £110,000 to £150,000. So an increase of about just under 40%, about 30%. And that's pretty cool. It should certainly help all those people who tell me that they can't get budget for performance testing, where we predicted here that if Cook improved that page by 1.5 seconds, they would improve their revenue by £40,000 a week. That'll buy you a lot of performance testing. So, and that's exactly what happened. I think it's amazing, which is why I keep repeating it. And this is a real example today of CXI. I should, of course, say that Cook did indeed, of course, go ahead and implement these performance improvements that CXI predicted. And the revenue increase they saw was 92% of what was predicted. So a pretty excellent prediction. And of course, there are lots of things to make sure, sort of isolate different factors and so on. So I really think that customer experience insights is going to transform testing. First, by focusing testing on what customers are doing and what they care about, customer-driven testing. So for example, rather than manually selecting the 100 test cases you're going to run each night and sort of update that selection every year, maybe we just use the 100 most common user journeys from production from the last 45 days, or the 100 user journeys that drive 80% of your revenue, or as another example, using real user data to set the thresholds of your performance tests. So rather than just saying, oh, let me know if a page goes over 3 seconds, say, let me know if a page takes longer to load, and that we predict that would therefore have an impact on the conversion rate of our website. So using CXI data to achieve true customer business-driven testing. Which is great. The second way, and I think the more important way CXI is going to transform testing, is CXI really enables us to remove that gap between testing and the business by quantifying the relationship between technical metrics and business metrics, so that we can focus testing on business results and also report in terms of business impact. As I sort of talked a little bit before in results analytics, really that was using the CXI concept of transforming technical metrics to business metrics, applying that to release analytics to really predict the impact of a new release, not only on users at a technical level, but predict the impact on revenue, predict it on the business, during that release meeting. And if that doesn't remove that gap between testing and the business, then I'm really confused. So, finally, I think CXI also creates the potential for testing to not just be about highlighting issues, but proposing recommendations. So for example, if CXI tells us that the usability of a screen is bad, and this is impacting conversions by 4%, by understanding the data, the models, the heuristics, testers will be able to propose optimizations to the development team. They'd be able to tell the development team, look, based on our analysis, based on what we've seen, based on the models we've trained, we believe if you guys make this change or you can achieve this outcome, this will impact conversions by 4% or 5% or whatever. And for me, this is starting to get towards where I think the human element of testing is going. Finding optimizations, not just sort of preventing failures and non-compliance with a specification, and finding business optimizations and user optimizations, not just technical things. So really adding to the mix those things that only a human can, and computers are never going to be good at. Now, there are definitely other areas where AI is going to have a big impact on testing, which I don't really have time to go into today, and some of them I think are well understood. Interacting with the physical world is clearly something where AI has a big role and is already playing a big role. Results analytics, I think, is another area. So, determining that of the 76 test failures we had yesterday, it's really 3 different root causes. There are 3 bugs. So don't raise 76 issues in Jira, just raise the 3, and imagine how much quicker that would make your sort of mean time to fix. Imagine how much better that would make that interaction between test and development, and of course gathering relevant diagnostic data about those defects. The screenshot here is from a product called AppSurify, and they're doing some really cool work in that area, so look them up. And I'm sure there are lots more areas where AI is having a big impact already today, and be fun to talk about them. Great, so that's it. The key message I really want you to go away with is that AI in testing is real, and it is going to transform testing over the next 2 years. It's going to help us automate more of the boring, repetitive tasks we don't like, help us focus in the areas that matter the most in terms of risk and business priority, help us predict the impact of changes before we release them, and help testers not only find issues, but also recommend solutions and optimizations. But there's nothing magic or scary about AI. At the same time, it also can't do everything. So please start looking at the interesting real AI technologies in testing, trying them out, participating in the discussion about how these things should evolve, and planning how you can use them. And the title of my presentation also said that these changes are all good for testers, which I really believe, and hopefully you've got a sense of that throughout the presentation. All of these approaches require human guidance, interpretation, domain knowledge, and of course just dealing with exceptions. Fundamentally, like all technologies, AI in testing should reduce the time we spend on those mundane tasks and increase the time we can spend doing all those things we talk about but never really do. So I'd just like to finish with a quote from Eric Siegel, who wrote the original book on predictive analytics. He's sort of the father of all this. And he said in his original book, art drives machine learning. Strategies designed in part by informal human creativity succeed in creating predictive models that perform well. And I think that's just a great place to end. So thank you for your time, and we'd love to hear from you.